Let's solve this really cool geometry problem from the IMO Shortlist. The incircle of the acute-angled triangle ABC is tangent to circle BC at a point K. Let AD be an altitude of triangle ABC, and let M be the midpoint of the segment AD. If N is a common point of the incircle and to the line KM, then prove that the incircle and the circumcircle of BCN are tangent to each other at the point N. So you might notice that we've defined a lot of extra points, but we'll go through those definitions one by one, starting with T and IA. IA, this is a pretty common definition, and IA is the excenter. Also, T is the and it's well known that N, K, and IA, those are collinear because of the M, K, and I are collinear because IA, K intersects the midpoint of the altitude. And so, since M, K, and I are collinear, all of N, M, K, and I are collinear. And T is the intersection of this line that connects all these points and the perpendicular bisector of BC. So you could say that all these points are collinear. And since T lies on the perpendicular bisector of BC, TB is equal to TC. So, what's the conclusion equivalent to? Well, it's by chapter 4 of the EGMO book by Evan Chen. We know that these two circles are tangent to each other at that point N if and only if B and CT is cyclic. And that's how the point T is defined, because T is the midpoint of the arc BC. And so if and only if N, B, T, C, those points are concyclic, then the conclusion holds. So that means that we want to prove that this black circle right here actually passes through all four of those points. And let's do this using power of a point and a very nice trick. So what do we want to prove in terms of power of point? Well, what's a logical candidate for the point that we do power of a point on? It looks like K looks good because there's those two lines passing through it. So basically what we want to prove is that NK times KIA equals to BK times KC. And so how should we prove this? And now let's define a point Z, because the point N is kind of hard to deal with because we don't really know anything about it. So let's define a point Z. That's the midpoint of segment NK. So then we can half this down to ZK, but we'll have to multiply KIA by 2. So this is ZK, which is half, times 2 times KIA, which is BK times KC. And now let's find 2 times KIA. Because, as it turns out, T is actually the midpoint of KIA. Also, define K prime to be the point of tangency with the AX center inside BC. Then we know that there's a homothency at K, bringing this point circled to K prime, because it's well known that K and K prime are flexions across the perpendicular bisector, and that homothency has scale factor 2. And so since KT and IA are collinear, also because these are both right angles, so the two sides are parallel. So then that means that there's the homothency with scale factor K equals to 2 at K brings T to IA. Therefore, T is the midpoint of KIA. So if we want to multiply KIA, this should not be KIA. We want to prove that NBTC is cyclic. So this should be KT. So we want to multiply KT by 2. And so that would just be KIA, because we have NK to ZK, so we need to multiply KT by 2. And so this is what we want to prove. And now this is the part where I like this is the part that I like the most. So what's this part equivalent to? Then what's this equation? Well, by PowerPoint on K, it's equivalent to the assertion that B, Z, C, and IA, those points are also this should be KC. Those points are all concyclic. And so how do we prove this? So this is pretty cool because it turns out that all of these points actually lie on a very special circle. So let's just put in the in-center right there, in-center I. And so we know that Z is the midpoint of NK. Therefore, since triangles ZIK and ZIN are both congruent, that means that by you can just use SSS similarity, that SSS congruency, that works, since and Z is equal to ZK. Therefore, angle IZK is equal to 90 degrees. In particular, angle IZIA equals to 90 degrees. And this means that if we draw this line right here and this line, this means that Z lies on the circle with diameter IIA. And so it turns out that so we want to prove that Z, B, I, and C are concyclic. And clearly IA lies on the circle with diameter I, with diameter IIA. So we just need to prove that B and C lie on this circle with diameter IA as well. So that circle that I knew, not an adjuster, should have diameter IA. And we need to prove that B and C lie on it as well. So let's just prove that B lies on it. And by symmetry, the same thing holds for C. So we need to prove that angle IB, I need to get out of this weird font thing. IBIA is equal to 90 degrees. And note that, let's just say that angle ABC is equal to X degrees. Then angle IBC, because it's an angle bisector, this is equal to X over 2 degrees. And since BIA is an external angle bisector, this angle is equal to 180 minus X, which is like, let's just say this point P somewhere. The angle CBP is 180 minus X, and so angle CBIA is 90 minus X over 2. So this angle is 90 minus X over 2. In particular, summing these angles yields that this angle right here is a right angle. And similarly, where this extends to I, not to Z. And similarly, this angle is a right angle all the way to I. So therefore, BZ, C, and IA all lie in the circle with diameter IAI. Therefore, it's well known that now there's a homothency at N. So now there's a homothency at N since T is the midpoint of arc BC, and so the conclusion follows. If you liked this video, please like and subscribe. Thank you.